I'm going to be talking about Pokemon and how all the different distributions we've learned in week 5 relate to that game. So, how this game works, the original computer game, again, there's multiple versions of it, but you basically find wild Pokemon in the grass randomly or in various locations, and some species are rarer than others, and you try to catch them with a Pokeball. So you throw a Pokeball at this random creature, and the species itself has a catch rate, which is a number generated between 1 and 255, and it also has a shake probability, B, which is some function of A, and it's between 0 and 65535. So it's 2 to the power of something high possibilities. And essentially what happens on the back end is the Pokeball basically performs 4 shake checks, and if it passes all 4 of those, the Pokemon is caught. So basically we have these inputs, and we could figure out the probability of catching a Pokemon once you find one. So how an individual shake check works is that the computer is going to randomly generate a number between 0 and 65535, and if that number is bigger than the number that belongs to the species that you're trying to catch, then the shake check fails. So it's basically like the higher the number, the higher the number the Pokemon has, the less likely that the number the computer generates is going to be bigger than it, and that the shake check fails. And so we could actually figure out the probability of passing that. It's going to be some function of B. And so essentially what we have is the number that the computer generates is a discrete uniform random variable on 0 to 65535. So we can use the probability that we know, or the CDF actually, to find the probability of passing the shake check. So the probability that the check fails here is the probability that X, the number generated by the computer, is greater than or equal to B, which we could take as 1 minus the probability X is less than or equal to B minus 1, because this is an integer valued thing that's being generated. And that, by definition, is just the CDF evaluated at B minus 1. Cool. Well, we know that the CDF of a uniform, f of X minus A over B minus A, where A and B are not the A's and B's from the Pokemon here, just A and B is the, if X is uniform on AB. So we're just going to sub those numbers in here. Here A is 0, so that's the 0 here and here, and B is 65536. And there's a plus 1 on the bottom here, sorry. B minus A plus 1 on the bottom, and X minus A plus 1 on the top. So we have B minus 1 minus 0 plus 1 over 65536 minus 0 plus 1, which is just 1 minus B over 65536. So that's the probability that the shake check fails, and thus the probability it passes is 1 minus that. So if we want to catch the Pokemon, we have to actually pass 4 shake checks in a row, and they're independent, and so the probability of doing that is this probability that we calculated raised to the power of 4. That's cool, great. But what's interesting is when you actually play Pokemon, the ball will shake a number of times, and it's like displayed that it's represented visually in the game. And if it's gonna fail, it basically shakes a few times, and then the Pokemon breaks free of the Pokeball and gets away. So we can actually find that as well. If we want to find the number of shakes, we can just find the distribution of the number of shake checks it passes before the first fail. So the number of passes before the first fail sounds an awful lot like a geometric distribution, right? When we're talking about geometric distribution, we think about Bernoulli trials, so independent, same probability of success, and we're counting up the number of trials that occur before the first success. So this is just like a reverse geometric. It's like the number of successes before the first fail. It's basically, we could say it's like a geometric, except success here is defined as fail or shake check. So we've just redefined what success and failure means, but it has the same basic idea. So it sounds a bit like a geometric. We're waiting for something to happen and counting up the number of trials that occurs before that happens. But it's not quite geometric, because here there's a limit. If it passes 4 times, then it doesn't keep going. It doesn't, it stops. The Pokemon is caught and everything is done. So we can think about it as like almost a geometric. It starts off like a geometric, but then it's kind of truncated, and then all of the rest of the probabilities go together to be the Pokemon being caught. So we can figure out for each of those possibilities what is the probability. of that number of shakes. So the probability of the Pokeball shaking 0 times means it fails the first check. So we know what that is already. The probability of 1 shake is the probability of passing the first and then failing the second. So we have the probability of passing here and then failing here. And then we can keep going. Here we have passing squared and then failing, and here we have passing cubed and then failing. So it's looking like a geometric probability function, right? We have like this p and then 1 minus p, p, 1 minus p squared times p, 1 minus p cubed times p, except here p is 1 minus b over 65536. So it's kind of, again, starting to look like a geometric with p equals 1 minus b over 65536. Yes, we are assuming the shakes are independent, and geometric and hypergeometric have absolutely nothing to do with each other. It's the worst naming convention. Whoever named these distributions needs a swift smack upside the head. But yeah, no, geometric is because the sequence of these probabilities is a geometric series, right? If you look at this, 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 and this, it's a geometric series with a common ratio of, I guess in this case, b over 65536, in general, 1 minus p. So it's a geometric series. Hypergeometric has nothing at all to do with geometric. It's one of those weird things that I wish there was a different name for it. Yeah, so thank you for asking that question, because a lot of people are confused by that, but they are not related at all. Geometric and negative binomial are very closely related. Negative binomial, and geometric all relate to Bernoulli trials. Actually, maybe once this is done in the Q&A, I can talk a bit about how to tell when to use which distribution. But yes, and here we are indeed assuming that the shakes are independent, because when the computer generates a random number between 0 and 65536, it does that independently each time. It's probably not truly independent. There might be some like pseudo randomness to it, but we are assuming that they are independent, and they basically are. Okay, so we've got our probabilities here for our geometric series so far, but then we know from before that the probability of catching it, which is what would happen if we don't shake 0, 1, 2, or 3 times, that's just b over 65536 all raised to the power of 4. So this last probability here is the probability of catching the Pokemon. And you can double check, please do, if you want, that those 5 probabilities add up to 1, which is kind of cool. So we have basically, it started off like a geometric, and then we took everything from like 4 passes and up and grouped that together as you catch the Pokemon. So these are going to depend on the value of b, which depends on a, and it also depends on lots of other factors in the game. So it's not quite as simple. So this a is going to depend on the species of the Pokemon, the health of that Pokemon, what kind of Pokeball you're using, whether you have any like special things that you've added to it. But here, if we have some various values of b, the shake probability, and then we can think about calculating the probability of each of these situations. So if b is its maximum possible value, 65535, then the probability you catch the Pokemon is super, super, super high, 99.994. And the other probabilities are very small. But I can just pick some other random value, not random, some other arbitrary values of b. If we have a 60,000, then the probability of catching it is 70.26%. 50,000, the probability goes down to 33.88%. 20,000 is very unlikely, less than 1% that you're going to catch it. And then again, we have all of these other probabilities just calculated using these numbers up here, which we got from essentially a geometric with the tail chopped off, basically, or the tail squished together. So that's one way that that these probabilities, these ideas that we've used in chapter 5, come up in this game. So we have kind of the uniform was involved in calculating the probability of a shake check, and then we have kind of a geometric, but also not here in this problem. But there's another way that the ideas from chapter 5 can be related to the Pokemon game, and this is the idea of the Poisson process. So we think about finding Pokemon in the first place, like that's what you have to do wandering around in the game or in real life in the world, whatever. The probability of encountering a wild Pokemon is basically like wandering around space and having events randomly occur. And that's kind of like the Poisson process. So we could do 2 types of things with this. We could imagine that there is just a Poisson process underlying everything in this game with a single rate lambda. And that's just going to sort of be, here's where Pokemon are, and there's this rate lambda, and you'll find one with this particular rate. And then once you find one, another random process occurs to some probability distribution for what species it is. So you might have some distribution and 1% of them are this species and 50% of them are this species, whatever. So the rarer ones have lower probabilities and the more common ones have higher probabilities. Lots of games work like this. My kids love to play these Roblox games like Pet Simulator or whatever. So you have an egg and then you open it. There's lots of gacha games like that too. You're drawing something and you open it and hey, it's a rare item, but then if you do it again, you get a super rare item instead, and that's better, whatever. Lots of games like this. So there's some distribution of what those Pokemon actually are once you find it. But the other way of thinking about it is imagining that there are multiple Poisson processes, one for each species of Pokemon, and each one is going to have its own rate. And the ones with rarer species are going to have lower rates, and the species that are more common are going to have higher rates. And the really cool thing is that both of these situations are mathematically and probabilistically exactly the same. It's just so neat. It's sometimes called the thinning property of the Poisson process. And if you are interested in that, I would suggest taking Stat 333 or 334 if you're in any of the Math Biz type programs or Farm. And actually even beyond that in 433, which is pretty advanced stochastic processes. So you can prove this. It's pretty neat, but you need some sophisticated conditioning that we don't quite cover in Stat 230. But if you're interested, you can post it on Piazza and I can explain it. But basically, no matter how you think about it, at any time you may encounter a Pokemon and it may be one of various different kinds of species. So let's just look at a numerical example. I'm just making some stuff up here. Imagine that you are saying that a Pokemon is encountered approximately, I will post that on Piazza. So approximately the rate is once per 2 minutes of playing time. I have no idea how accurate that is. And so we would say in that case that lambda is 1/2. Remember, when you're dealing with a Poisson process, the rate is always given as a number of events per unit time. Right? That's what a rate is, a number of occurrences per time. So if we're saying one Pokemon every 2 minutes of game time, that's a rate of 1/2. And so and we know this is actually true. The chance that a Pokemon is shiny in certain versions of the game is 1/8192. So basically, a shiny Pokemon Poisson process, so if we're looking at only the shiny Pokemon process, so ignoring all of the other ones, the rate is going to be proportional to the rate of finding a Pokemon in the first place and the probability of it being shiny. So it's going to be the product of those two things. The rate lambda of finding a Pokemon at all times the probability that the Pokemon you find is shiny. This again, I said believe me, but I will post the proof on Piazza. It's cool, but it's a little beyond what I would expect you to know for this course. So we have this very, very, very small rate at which you are finding shiny Pokemon. So imagine we want to calculate the probability of finding at least one shiny Pokemon in 12 hours of game time. Well, we're going to do the same process we always do for calculating a probability involving a random variable. First, we define the random variable. So we're going to let x equal the number of shiny Pokemon found in 12 hours of game time. And the second thing we want to do is figure out what distribution x has. Well, here we have a Poisson process with a rate 1/16,384. And we are watching this process, observing this process for a fixed amount of time, 12 hours. And we want to know how many events occur. So by definition, if we have a Poisson process and we're watching it for a fixed amount of time and wondering how many events happen, that is a Poisson random variable. So we know this is a Poisson random variable because it follows those conditions. And the parameter for the Poisson distribution here is lambda times t. So the rate at which events occur times the amount of time we're watching this process. But we have to be careful because the rate here is given in minutes, but the playtime here is given in hours. So we just have to make sure that we're being very, very careful about our units. So we have lambda here, that's our lambda, and t is 12 times 60 because there are 12 times 60 minutes in 12 hours. You have to pick to use minutes or hours. And altogether, we end up with a Poisson distribution with a parameter of 0.0439. So that was step 2, figure out the distribution and parameters of it. And then finally, the third step is to find what we want. We want the probability of at least one shiny Pokemon in these 12 hours. So the probability of X being greater than or equal to 1, in this case, we could just take that as 1 minus the probability X is equal to 0. That's easy. So that's going to be 1 minus e to the negative the parameter times the parameter to the 0, which is 1, divided by 0 factorial, which is also 1. So those disappear, and we end up with 4.3%. So even after 12 hours, it's super unlikely that you would find a shiny Pokemon. All right, so there's, again, yet another way that the Chapter 5 material can be applied to the game Pokemon. And of course, in the game, it probably isn't exactly a Poisson process. It probably isn't truly, independent, constant rate, and singular. Actually, it's probably not too far off, those assumptions. Like, you can't bump into two Pokemon at exactly the same time, I don't think. Maybe you can, and then it's not quite a Poisson process. But anytime you're using something to model a real phenomenon, it's good to think about how closely the assumptions will hold. They'll almost never be perfect, but they might be close enough that this is a useful exercise. And this is another great application of the Poisson regression model. So this is pretty, there's some stuff in here that you won't learn about formally until Stat 231, so hopefully I'll pique your interest for Stat 231. But just to recall, the idea of regression is where it's a machine learning problem where you want to assign a numerical value to some object based on its characteristics. And that's very vague and broad for a reason. Regression can be applied to lots and lots and lots of different situations. So in this case, we're basically trying to take some things we know about an object and use that to predict a numerical value about it. One particular type of thing that we might want to predict is the count of something. So looking at the number of things, sorry, my face is in the way. There we go. The count of something. In other words, like the number of events, the number of occurrences of some event in some future time period. And often we do this like sequentially. So the number of students walking through the SLC expansion per day, which I mean, right now it's probably 0 because it's still under construction. But in general, that might be useful for like marketing or just anyone would want to know this, how many people pass a certain spot per day to know where the optimal place to put an ad is, maybe something like that. The number of cars passing through an intersection per hour. So that, be useful for a traffic study to know whether to, put a stop sign somewhere. Thinking about the number of vaccines given out per week. That's very relevant nowadays. Or the number of financial transactions that occur per minute. So often this is something that occurs multiple times, and you might be interested in predicting the future behavior of something like this, which is known as a time series. And in this case in particular, we're looking at the number of something. So this is a count data because we're counting the number of things that happen. And all of these examples that I gave have in common that they make some sense to be modeled by a Poisson distribution. So what's true about all of these things is that they're non-negative, right? You can't have -1 person or -1 car. They're integer valued. You can't have half a financial transaction. You can't have half a car. Can't have half a student. Could have half a vaccine dose, I guess, but whatever. And there's no preset maximum. So we know that the binomial distribution, for example, still satisfies the first two things. It's non-negative and it's integer valued, but a binomial has a preset maximum because there is a number of trials that are done and then it can't possibly go higher than that. Whereas the Poisson has no maximum. So that's a useful feature of this data. In fact, there is another distribution that also has all of those properties. That's the negative binomial. And often both of these are used and sort of see which one fits better. When we get to Chapter 7, we'll talk about mean and variance. And something about Poisson that's interesting is that the mean and variance are equal to each other. With a binomial, the variance is always less than the mean. And with a negative binomial, the variance is always larger than the mean. So if that means nothing to you at all, don't worry about it. We'll see it later. But based on some sample data, you could basically guess which of these distributions might be more appropriate based on the relative sizes of the mean and variance. But for now, we're going to focus on the Poisson because, again, it's a reasonable distribution to use to model these things. And suppose we've got some data. So we've been collecting some data on the number of cars passing through an intersection or the number of financial transactions, whatever. And we call that the training set. So this is a supervised machine learning problem because we have this data already, and we know what the answer is for that data. So we could basically look at the data and estimate the rate for this Poisson process over 1 unit of time, and then we would essentially guess that the future occurrences are going to follow that distribution as well. So the probability of observing Y events in 1 unit of time is e to the negative lambda times 1, so I just dropped the 1, lambda to the, oh sorry, that should say k events, not y events, my apologies. So e to the negative lambda, lambda to the k over k factorial. We can call it y or k, it doesn't matter. The problem with this is it's a little bit unsophisticated. It's assuming that the rate lambda is constant over time, which in some cases may be reasonable, but over the long term, it's probably not the case. Right? Over the short term, it's probably reasonable that the rate is relatively constant, but there might be trends, right? There might be more people walking through the SLC on a school day than a non-school day. There might be more financial transactions during business hours versus during non-business hours. Whatever, there's lots of different reasons why this rate might not actually be constant over time. So this is where the idea of the Poisson regression model comes in. We want to take this idea of a very simple Poisson model with a constant rate, which is the one that we deal with in this course, and add the machine learning element to it about regression, where we want to take some characteristics of the objects, of the days that we're trying to predict, and then use that to influence what our prediction is going to be. So imagine we have some of these characteristics that could influence the rate lambda, and they could be different for each day or time. And those are called lots of different names. Regressors, people call them explanatory variables, people call them explanatory variates, people call them predictors, people call them independent variables. There's a million names for them, but I'm just going to call them regressors. And there could be more than one, right? There could be like, say what day of the week it is, like, or just a binary variable for weekend versus weekday. It could be the weather. So like whether it's a category or an actual like number for the amount of precipitation that day or something. So there's lots of different characteristics that we could model about a particular day that we're trying to predict the number of events occurring on it. And we collect all of that information and put it in a vector. So for day I, the collection of explanatory variables or regressors is a vector xi. And then what we want to do is imagine that the rate for day I is now allowed to change day by day. So we're now no longer assuming a constant rate. We're going to assume a rate that's allowed to depend on the day. So we'll call it lambda I as some function of these characteristics. So it might be some function of what day of the week it is and what the weather is. And there's a million, more than a million, there's an infinite number of choices for what that function is. But one thing that works pretty well and one thing that characterizes the Poisson regression model is we take e to the power of this vector xi multiplied by another vector beta, where a beta is just a vector of parameters, sometimes known as regression coefficients. There's also lots of names for that. So that's a basic idea. We sort of say some function of these xi's, these explanatory variables, and some parameters, beta, we take this function of it, and that is the rate, the Poisson rate that we think is going to apply for this particular day. And there's lots of statistical packages like R or Python that can estimate the best possible choices of beta to give the most accurate prediction. In fact, that is essentially the entire point of Stat 231, the idea of figuring out the optimal values of beta to use in any kind of regression model. I put a little star here at the bottom, Stat 231, and many higher level stat courses deal with tons of ways to do prediction like this. So you could do maximum likelihood prediction, you could do method of least squares prediction, you could do method of moments estimation, you could do Monte Carlo, Markov chain Monte Carlo methods. There's like a lot of different ways to get at what we think is the best possible values for these betas. But once you have them, that's what you then use to make your prediction. So once we have that, we have on some future day, day I, we take the values of these regressors. So we're trying to predict, say, for Monday when the weather is 20 degrees. Those are a very small list of predictors. We plug those xi's into the function here, e to the power of xi times beta, with those betas, those values that were estimated by the algorithm. And then that gives us our rate lambda I. And then we do the same thing as we did before. The probability of k events on day I, given those characteristics, so given those particular characteristics xi, is the same thing as it was before. The only difference is we have lambda I here and lambda I here, because it's a specific lambda for that day, which is based on those characteristics. So that's it. You basically can predict the distribution of the number of events that are going to happen on day I using the characteristics that you know about day I. And that function, again, comes from lots of cool different methods. Gradient descent is another one, to try to find the best possible choices of those betas. There's lots more technical stuff that goes into it, and I have a link to a cool demonstration of it with some data on the number of cyclists that went across a particular bridge. So we're keeping track of how many cyclists went across a bridge on each day, and then they also kept track of things like the weather and various other things. And so you can build a model like this with Python, and I'll post a link to it on Piazza. All right, if there are any questions, please let me know. I saw one already. Since the rate differs, would it be feasible to make multiple models with differing rates? Exactly. Yeah, that's basically what we're doing. Yeah, we're sort of saying it's still kind of one model, sort of, because it's always the Poisson model, and we're always keeping those same regressors, and we're keeping those same coefficients, those betas. But essentially, yeah, we're basically saying the rate is different on this day than it was yesterday, but not just randomly different. It's different because we have this extra information, these characteristics. So the machine learning happens in maybe identifying what those characteristics are, and in lots of different ways for estimating the best possible choices of beta given those explanatory variables. Okay, if there are any other questions, please let me know. I just thought this was a really neat machine learning application of the thing we talked about this week, which was the Poisson distribution. Again, for us in this course, we will always be assuming a constant rate lambda, but we know in practice that that's not always true. And often questions in the course notes and on your midterm, hint, hint, will ask you to critically evaluate whether you think that's true, whether you think that the rate lambda is actually going to be constant in real life for this situation. And that's important to think about, because a model is only as good as it matches the characteristics of what you're trying to model, right? If you have a beautiful model that is nothing at all like reality, then the conclusions from it might not actually be particularly useful. Oh, another question. Yeah, since a Poisson process is based on a constant rate, could it be used in error correction codes, predicting bit flips? Oh, yeah, definitely. Yeah. So that would be a great marriage of two different ideas. Yeah, awesome. You totally could do that. Yeah, we had said it was binomial, basically, like each bit could either be flipped or not, but it might be a little more accurate to assume that like errors occur in the string according to a Poisson process. It's like the Poisson process is theoretically continuous, as in like an event could happen at any time, but you could definitely have periods where there's more errors, like maybe in a storm or something, an electrical storm, maybe there's the connection is noisier, or if it's, multiple people are trying to use the same internet connection at the same time, like everyone's trying to write a midterm at the same time, all living in the same building, then maybe the connection would be more unstable at certain times than others. But again, for this course, we are always assuming constant rate, but it's still a good idea to think about whether that would actually hold in real life or not. Oh, I saw a question first though. Yeah, I'll do the question first. Could you please explain the strategy to solve question 1D, computer assisted assignment 1, question 1D? Is suppose a person tests negatively twice, and we assume the tests are negative. The test results are independent within an individual given their disease status. What's the probability they have COVID-19? So this is actually very, 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 very similar to the week 3 swag that we did, where we were talking about spam and then different characteristics. So we're assuming that the characteristics were independent based on whether the message was spam or not. So I'm not going to go through it in a ton of detail because that would basically just tell you exactly how to do it. But what you want to do is think about that exact same thing. So what we're told is that test results are independent given the disease status of the individual. And that's, again, the exact same thing as what we did 2 weeks ago with the spam message. And then we had been assuming that the various features of spam message, spam messages are independent given the type of message that it is. So it's the same idea as features, whatever, of suspicious emails are independent given the message is spam or not spam, or not. So it's the same thing that we're assuming, right? That basically the idea of conditional independence. So given something, these two things are independent. And if we say A and B are independent given C, which is exactly what we're saying here, that means, so that implies in both directions, that P of AB given C is equal to P of A given C times P of B given C. This isn't defined anywhere in the course notes because it's not a new definition. This is just the same definition as independence, but now everything is conditional on C. So the probability of A intersect B conditional on C is equal to the probability of A conditional on C times the probability of B conditional on C. It does not mean, though, that A and B are independent. So P of AB is not equal to P of A times P of B. And that's not like triple factorial. I'm just extremely excited about this. Or not even excited. Excited is the wrong word. I'm very emphatic about this fact. So being independent conditional on C is not the same thing as being independent. That's why it's phrased the way it is, that the results are independent given the disease status of the individual. So if A and B are your test results from the first and second test respectively, and C is whether or not the person actually has the disease, then this is the result that you want to use. And then again, what we're looking for in question 1, part D, is suppose they test negatively twice, what's the probability that they have COVID-19? That's exactly the same question. So I'm gonna scroll down here again. Suppose they test negative twice, and then we want the prob that they have the disease. That is the exact same question as suppose that the message had all of those features, of a spam message. We talked about, failing an RDNS check and a couple of other things, being sent to over 100 people and having a link that doesn't send you where you're supposed to go. The probability it's spam. So again, this is the exact same thing that we're asking here. Given we have these two negative test results, what's the probability we have the disease? Or equivalently, given the message has these features, what's the probability it's spam? So for that, you want to use Bayes' rule because we have information about test results given disease status, and what we want is results about disease status given test results. And anytime you want to swap the direction of the conditioning, that's where you use Bayes' rule. So I'm just gonna leave it there. Again, not factorial, because that's what's gonna let you to calculate the probability of having the disease. So let's say C, given that you tested negative twice, A and B. I'm deliberately not using the same letters that the question uses because I want you to actually think about it yourself. So that's what we're looking for, the probability of having the disease given both of these tests were negative, equivalently the probability of being spam given we had these features, and then you want to use Bayes' rule on that. So you hear, right, this is going to be the probability of both, so the probability of C times the probability of AB given C divided by the probability of AB. Scrolling some more. But this, you can't just calculate it by taking P of A times P of B because that is not true. Not true. So you have to do that denominator. Again, you'll have to do what we did for the spam example, split that up into two cases and evaluate each one. I'm going to go flip over and then talk pretty quickly about the midterm. So it's posted yesterday evening. The midterm is on Thursday, February 25th, as originally given in the course syllabus and everything, and it covers up to the end of this week. So up to today, including, well, which is just chapters 1 through 5 in the course notes. It's going to have 2 parts, and I see a question there, so I'll get to that in just a second. The first part is a 15 questions that similar to what you're used to seeing, short answer or multiple choice or true false type questions in Mobius. And the question, how hard will the midterm be in comparison to the Mobius quizzes? The Mobius part will be basically the same. Like we're essentially drawing questions from the same bank of questions for the midterm. There'll be someone that you haven't seen yet, so that's fine. But it's certainly the multiple choice and short answer questions are similar difficulty level to the ones that you've been seeing on the quizzes. The difference, though, is that here you only have 1 attempt. So just keep that in mind. Like if you were generally doing well on your first try at those Mobius quizzes, you'll probably do reasonably well on this midterm. If it was taking you 3 tries to get a mark that you were happy with, you might want to prepare a little bit more for the midterm because you do only get 1 shot at it. And just like all of the Mobius quizzes, it's the same format, so you can only navigate forwards through the questions. And you'll have enough time to be able to do that, and you know how many questions there are, so you can pace yourself, but just keep that in mind, that you can only go forwards as usual, but this time you only have 1 attempt. But the questions are no more difficult systematically than what you've seen on the quizzes so far. The second part is full solution questions. So there'll be 3 of those, and they'll be delivered through Mobius, just so we can randomize them. And you have to basically answer on Mobius, but also put your solutions on CrowdMark. And that is so that we can give you part marks for if your final answer is incorrect, but you've got some correct process. And also there's some like written answer, so like things that require you to graph something or explain something in words, and that is basically impossible to mark on Mobius. So we're sending that through CrowdMark instead. The question then just came in, what platform do you use for part marks? That's the CrowdMark. So you'll take your Mobius the Mobius questions, you'll get them, take a screen cap or copy out, whatever you prefer, the question from one to the other, and then answer them, and then submit your solution to CrowdMark and your numerical answers to Mobius, and then we'll mark them both, I guess. For that part, you can navigate forwards and backwards because if you forgot to copy the question or you wanted to work a little bit more on one and go back, because these are 3 long answer questions, we wanted to allow you to move around. Question also, do we get full marks for right answer but wrong solution? So if it's a proof, no, but I don't know if there's going to be any proofs. There might be, but so it would be impossible to get full marks by only submitting on Mobius because many of the questions require you to draw something or answer something in a sentence. So for those parts, no, of course not. You couldn't get perfect if you don't have a sentence. But for the most part, yeah, I think we've designed the question so that the only way to get the right numerical answer is to do the right solution. But you should still definitely write out your solution. Like, don't just not write it. We'll check both of them. But thank you for asking. So that's the idea. We sort of have 2 parts to the midterm, one that's similar to the Mobius quizzes and one that's a bit more like questions that we would normally ask on a midterm, basically. More similar to past midterms that are out there. It is open book, just like the quizzes, so you can access anything on the course website, including watching videos if you want to, or anything on Piazza, but please don't consult external websites, or certainly don't talk to any other people. It has to be your own work. And to help with this, all the questions in both parts are identifiable. So if a question shows up somewhere, we will know who posted it. There's enough parameters that we can put in so that each person will have completely unique questions. So just to make sure that what you submit is your own work only, it'll be, each one will be identifiable. And in terms of the timing, again, we would expect a well-prepared student to be able to complete the entire thing in 90 minutes. So like in class, when we do things in person, we usually give 90 minutes for the midterm, but we've given double that. So we're sort of giving you 90 minutes for each part, where we think it'll take you 45 for each part. And so just that's helpful for if you have slow connection and it takes some time for the page to refresh, that you're not at a disadvantage. So You can also do those two parts in either order. So you can do the short answer multiple choice ones first and then the long answer. I think I would probably recommend that. But if you prefer the other way, absolutely, you can do the full solution first and then the short answer ones. And you can do them back to back, or you can take a break in between. Totally fine. Might be a great idea to do one part, and then if there was stuff that you struggled with, go study some more and then do the other part. Hey, it's like you get a study break in the middle of your midterm. But once you start each part, you have 90 minutes to finish it. So don't open them both at the same time, because then you're basically running out the clock on both of them simultaneously. That's like challenge mode, I guess. If you really, really want the in-class experience, you can open both parts at the same time, and then you only have 90 minutes for the entire thing. I do not recommend that. Please don't do that. But yeah, we want to give you the flexibility to do it all at once or in breaks, and you can do them in either order, whichever you prefer. It'll be available, the whole thing will be available the entire day, basically, on Thursday, February 25th. It'll open 11:59 p.m. the night before, and then it'll be available until 11:59 Thursday evening, all times Eastern Standard Time. And we did post a practice version of part 2, may find some more. There's tons out there. Part 2 is very similar to any in-class midterm, so you could look for any of those. And we're working on sort of a practice part 1, just to give you more chances to try and prepare. So, that's the basic idea for the midterm, and I would welcome any questions if you have them now. It's still, again, almost 2 weeks away, so you may not be thinking much about it yet, especially if you have not yet finished the computer-assisted assignment, which is due tonight. But hopefully at some point during reading week, you get the time to start preparing for this midterm, and you can use the practice materials that we have to gauge your level of preparedness and make sure that you're as prepared as you want, so that you get a good result that you're happy with. Are there any other questions about the midterm? Oh, is there a timer on CrowdMark for part 2? So that's a great question. So no, CrowdMark doesn't have a timer. We might be able to set it up with one. I'll have to look into that. That wasn't our intention, though. Basically, what your limit would be, so you open the Mobius quiz, that gives you the questions. Part 2, the part 2 Mobius is where the questions will be delivered to you. And then you have to make sure that your answers go into that by the time that is up. And then a reasonable amount of time after that, having your stuff submitted to CrowdMark. So maybe we'll say within half an hour or within 15 minutes or something like that, that your stuff goes into CrowdMark as well. So we'll know when your Mobius timer is, and we'll know when your CrowdMark submission was. And if those are more than half an hour apart, just don't make them be more than half an hour apart. Something will happen, I don't know what, but you'll be expected to upload your solutions within 90 minutes plus epsilon, where epsilon is a reasonable amount of time that we think it might take to scan and upload to CrowdMark those pages. And again, as long as it's within reason. Like if it's like, if we say half an hour and you're 31 minutes, we're not going to go like run after you. But if you're 4 hours later, yeah, no, that's not cool. Well, I want to sort of take the last few minutes to recommend that you take care of yourself over reading week. I want you to know that it's a good idea to set goals for yourself over reading week, but some of those goals should be non-academic. Like some of them should be personal, self-care related, like interpersonal, like talking with friends or family online, playing a game, maybe creative, like drawing, or active, like going for a walk every day or something. So reading week is an opportunity to like catch up or get ahead, maybe even on your academics, but it also should be a time that you deliberately take some time to relax. And if your goal for yourself for reading week is to relax 100% of the time, and you achieve that goal, that is worth celebrating. So I am going to post the last sort of thought question on Piazza for this week to be, what do you want to do over reading week? What are your goals for reading week? And again, those could be things like study for the midterm or review the material, but they could also be read a book that you've been meaning to, or listen to a podcast, or try a new video game that's been like your friends have been playing but you haven't yet, or get together with a bunch of friends and play together, like play Among Us or something. Like do something, deliberately schedule time for yourself to have fun and relax, and make sure that you're getting enough sleep and drinking enough water and getting exercise and all that stuff, but take some time to actually relax and have some fun. So I'm going to post some suggestions on goals that you could set for yourself, and I'm going to ask if you're willing to share your goals, and then hopefully you have a good hopefully you're happy with what you accomplished over reading week. And again, everyone could be different. If your goal is to do no work and you do no work, you have achieved your goal. If your goal is to relax part of the time and do work some of the time and you do that, awesome, you have achieved your goal. So you don't want to just look back at the end of reading week and regret how you spent your time. So make some goals for yourself and try to stick to them. And then I'll check in once everybody's back on the 22nd. Oh, I see a question. Any suggestion for how much material we should cover during reading week? So it would depend on the course, I think. And what I would say is it would be a good idea, I think, to do some preparation for the midterm for this class over reading week. So make sure that you have watched all the videos from weeks 1 through 5. Again, hopefully you've been mostly keeping up with them. But just make sure that you've got all of that material under your belt. And then if you want to, maybe try the practice midterm that's posted, but you could also leave that until after reading week. It also depends on what else you have going on with your other courses. If there's some courses that you're really behind in, or some courses that have a big assignment due soon after reading week and you want to focus on those more, that's totally cool. If you don't do any Stat 230 stuff over reading week, not a big deal. But if you're doing fine in your other courses and you want to spend some time on this one, then yeah, just the first 5 weeks is what's covered on the midterm, so making sure you have a good handle on that. And I have a fun activity that can help with it. When you're walking around or just living your life, watching a TV show, playing a game, probability is kind of everywhere. Almost all the questions I've ever written into the course notes or on tests were things that happened. There was a thought question about someone getting on the Ion. I saw someone get busted for not having a ticket on the Ion. This was back in the before times. And I was like, that would make a great Stat 230 question. And my kids were playing a game with each other that they had made up, where they're basically standing on these cushions and jumping back and forth between them. But if they land on the same cushion, then they're both out. I was like, I wonder how I could model the probabilities in that game. So maybe it's just my brain, but I see probability everywhere. So my suggestion for the best way to get good at chapter 5 material, the idea of all of these random variables, is to look at situations around you and think what distribution would be the right one to model this situation. So if you want some homework, if you want a task from me over reading week, anytime you see something I wonder what distribution this would follow, either write it down somewhere or just try and remember it, or type it on Piazza if you want, and see if you can think about how the stuff in chapter 5, all of these different distributions that we've talked about, relate to your world. Well, thanks everyone for joining me today. Best of luck over reading week. I hope you have a relaxing and or productive, whatever you think is best for your situation, week, and get some good self-care and get some good sleep, drink enough water, do what you want to do, accomplish what you want to accomplish, and it is helpful to actually explicitly set goals for yourself so that you can see whether you're achieving them. And those goals can, again, be completely non-academic, or they could be all academic, or anything in between. Have an awesome day. Have an awesome weekend. Don't forget to submit your assignment tonight, and I will see you after reading week. Bye.